Alright, so after learning some theoretical details about testing a hypothesis from my general understanding video lecture about testing a hypothesis, then in this video lesson here, let's look at how we can do a few example problems regarding testing a hypothesis about a proportion value. So again, this video lesson here is showing different examples about how we can do testing a hypothesis on a population proportion value. And I would like to address that this video lesson is aimed at focusing on the steps of how we can test a hypothesis about a population proportion value, and some detailed explanations about how the steps are connected, as well as why a particular step must be taken and done as shown or skipped in this video, because those details will be given in a more advanced course in statistics. And so let's now look over to the wording descriptions of each of our examples here. So here I call that example 1, but each example is one actual problem on its own, where we can treat each example here as one independent problem. We may see throughout the video lesson that these examples have similarities in terms of the given information. However, again, as I said earlier, each example here is one independent problem on its own. So right now, let's have a look at our example 1 here. A sample of 396 cell phone users show 300 of them are iPhone users. At significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is more than 30%. So as a brief explanation, in this testing hypothesis, we would like to test a hypothesis about the proportion of iPhone users in the population. So any one of us is using a cell phone of some kind, and iPhone is not the only kind of cell phone we're using out there. There is there are Samsung cell phones, there are Nokia, there are iPhones, and there are so many other mobile phones out there. So we would like to study about the proportion of iPhone users in the population of cell phone users. And that's the aim of this particular problem here. So now what we have here is a sample of 396 cell phone users. And in this sample, it shows 300 of them are the iPhone users. But so now, right after reading the wording description of this problem, and after we have learned some understanding some general explanation about testing a hypothesis from my general lecture, then immediately what caught my attention here is that this question of the problem is a yes or no question. The question itself is saying, is the sample showing strong evidence that proportion of iPhone users is more than 30%? So in the end, this is a yes or no question. We want to find out whether our sample here, 396 cell phone users showing 300 of them are being iPhone users. This sample over here, we want to find out whether the sample is showing strong evidence that the actual proportion of iPhone users is more than 30%. So in the end, I just want to point out that from what we have understood about the general lecture, then this question here, this kind of question being a yes or no question, brings us right into a problem where we call that as a testing hypothesis. It's a sign right here. This question is a sign indicating that we are working with a testing a hypothesis problem. And now I'm going to undo the highlight right here. Let's look further into the wording description of this problem and extract some more information. So again, from the understanding we have already drawn from the general lecture, when I introduced about the general idea of testing a hypothesis, then if we focus right here to the question that says proportion of iPhone users is more than 30%. So this is the main statement that we are trying to prove here. We want to use a sample to prove whether we have strong evidence that the proportion of iPhone users is more than 30%. So now on my writing board, I can define the proportion. Lowercase letter p, as we have already understood what it means, we define that to be the proportion of iPhone users. And this proportion here, once we have defined that right from the statement of our testing hypothesis problem, then we have the following alternative hypothesis. From what we understand from the general lecture, H1 is the alternative hypothesis. And so in the way it says, we want to write P being more than 30%. So P is greater than 0.3. Because the statement is saying, as I highlighted it earlier, we want to prove that P is greater than 30%, and 30% is written formally as a 0.3. So this is right from the wording of the problem right here. And then right from that, right after successfully identifying our H1 hypothesis, our alternative hypothesis, we can easily come to our null hypothesis as a statement saying that P equals 0.3. And so again, from the explanation I have delivered in my general lecture about testing a hypothesis, it's always easier to identify the alternative hypothesis because it's right from the wording description of the problem. So again, in this wording description of our problem, this statement is what led me to having that H1 hypothesis, that alternative hypothesis, stating that proportion of iPhone users is more than 30%. And then according to what we have learned, after we have found the alternative hypothesis, then coming up with the null hypothesis would be a lot easier. It is simply just the exact or pretty much the same as the alternative hypothesis, but having the inequality replaced by the equal sign. And so now after we have successfully identified the two hypotheses here, H sub 0 is the null hypothesis, H1 is the alternative hypothesis. The inequality right in this alternative hypothesis is pointing to the right hand side, or in another way of saying, this inequality is showing greater than. And so for now, the test we're about to use, the test process we're about to use is called a right tail test. And so anyone viewing this video lesson will have a better explanation about why we're regarding to this test as a right tail test, or how a right tail test here will affect the later steps. But for now, what rings a bell for us, what's indicating for us to know it's a right tail test is that simply the inequality in this H1 hypothesis is pointing to the right hand side. As I said earlier, this inequality is pointing greater than, pointing to the right hand side. And that's one connection for now that's indicating we are proceeding as a right tail test. And now back into the wording of the problem. So let's now look at the sample that we're having. And again, from our understanding from the general lecture about testing a hypothesis, then a sample we used in a testing hypothesis problem is going to be our evidence. So in this sample that we have right here, according to the wording, a sample of 396 cell phone users shows 300 of them are iPhone users. So immediately right from this, as a quick little scratch work right here, I can have the following. Out of 396, I have found, so this is the number of all cell phone users in our sample. I have found 300 of them being the iPhone users. So this is a successive count, the count of iPhone users existing in our current sample. So what we have here is a sample proportion. The sample proportion of iPhone users in a sample of 396 cell phone users. And so the sample size in this case, capital letter N, will be 396. So that is some scratch work that we can write it down right here. And so now I'm going to formally write this as part of the steps of our problem right here. So our sample has sample size 396, and the sample proportion, reflecting the proportion of iPhone users in this sample, is 300 out of 396. And let's write this as a decimal value in 4 decimal places. My calculation came out in 4 decimal places, 0.7576. So this is the proportion of iPhone users in this sample. Take note that I rounded, in this lesson, I rounded this sample proportion to 4 decimal places, but do watch out for your rounding requirements in each problem that you're doing regarding the value of your sample proportion values. So now what we need to realize as the next step, and allow me to write it down in a little scratch work here as what to know. This sample that we have here at size 396 is not the only sample that we can find. There are infinitely many other samples out there. So indeed, what I want anyone to realize here, we don't have to formally write this down, but it's good to acknowledge this, that we can define, as soon as we pick a sample over here, we can define a random variable capital P hat 396 that represents, so any value for this random variable is the proportion of iPhone users in a sample of 396. And 396 here, I mean 396 cell phone users. Whereas generally, so here my count is 300 out of 396. That is one value of this proportion of the iPhone users. And then what we have here is a distribution of sample proportions. So now I'm going to write it down formally right here. Capital P hat 396, something for us to realize. This P hat is one of the values of this variable, this random variable. So capital P hat 396 is the proportion of iPhone users in a sample of 396. So this step can be skipped in some problem. What matters is, the reason I put it down here is because I want anyone learning from this video lesson to understand that this is something that we always have to realize, that our sample proportion that we currently have is simply just one among the infinitely many other sample proportions out there, where I generally regard any of those as a capital P hat 396. And so now the next step here is going to be a critical step, where I will be able to put in some better explanation as at the end of this particular problem right here, at the end of this testing hypothesis problem. So the sample size that we're currently using, or the size of each sample in our distribution here, 396. I am going to multiply this sample with, allow me to write this in red ink right here, 0.3. So this is the sample size, capital letter N. I am going to multiply that with 0.3. So 0.3, I wrote that in red, hopefully to catch the viewer's attention, that this 0.3 is the value being claimed in the null hypothesis. So the sample size multiplying with 0.3. This product will give me a count. This count came out to be, according to my calculation, 118.8, which is well above 10. So I call this a requirement check, and we will get a little better understanding of why we have this requirement check here as I move on through the steps right here. But this is not all of the requirement check steps yet. The same sample size, 396. 396. I am going to multiply with, and again, allow me to write that in red ink, 1 minus 0.3. So 0.3 came from the value claimed in our null hypothesis. So now I have another product to multiply. 396 multiplied with 1 minus 0.3. And so keep in mind, 1 minus 0.3 is numerically 0.7. So my calculation will come out as following. 277.2. So this count came out from multiplying our sample size with 1 minus 0.3. And again, the 0.3 came out as from our value claimed in the null hypothesis. And this count now is again above 10. So now this is what's important about this step right here. There are two calculations in this step, and each of the calculations you have already seen that right through my steps right here, so there's no need to repeat that. But the answer to each of the calculations here, once it has passed being above 10, like say this one here, 118.8 is greater than 10, and the other calculation result is also above 10. As long as we pass these two requirements, that tells us that this test, the sample that we use here, can be used further into the testing. So again, I repeat, once we pass the two requirements here, passing the two requirements here tells us that the sample we use here is a legitimate sample. It's a good sample that we can use to further proceed on our testing hypothesis problem. And at the end, I will be able to point out what's going to happen if the sample we have fails the test. But hold on to that thought to the end after I finish with the testing. But now again, our sample here passes the two requirements in order for us to proceed on with the test. And so now as the next step, after knowing that our sample passes the two requirements so that we can proceed on, then now we can imagine, now we can officially say that all sample proportions, so back to this capital P hat 396 that I put in your awareness earlier. We don't have to formally write this down in every step we're doing, but you gotta put it in the back of your mind somewhere that our sample is one value among this entire population of sample proportion values. So once our sample size has passed the two requirements, being given a product that's above 10, once we pass that requirements about our sample size, then it's indicating that all of these sample proportion values can be placed on a bell curve. And the center of this bell curve will be 0.3, which is exactly the value being stated in our null hypothesis, the value being claimed in our null hypothesis. This bell curve will have sigma, an average spread, where I call that sigma p hat. The value here can be found by taking the square root of 0.3 times 1 minus 0.3. And we divide that by the sample size, 396. So the value that I keep writing in red ink right here is so important. It all came out from the value that we claim in the null hypothesis. Calculation of mine shows that sigma p hat, the average spread for this bell curve, will equal, in 4 decimal places, 0.0230. And I use 4 decimal places rounding here, but watch out for your rounding requirements about sigma p hat on any testing hypothesis problem. But again, this bell curve now is officially representing all sample, the distribution of all sample proportions. And so think about the left and the right are all different values of a sample proportion at size 396. So we can label our random variable here, capital P hat, 396 here. So now let's put the picture here for now, and let's move on to the next step, and we will come back and use the picture for explaining our calculation. And now that we have had our bell curve representing the distribution of all sample proportion values here, our sample in particular, being a 0.7576, will be known on this bell curve, will be known to be somewhere on this bell curve. And precisely it should be somewhere to the right hand side, because 0.7576 is well above 0.3, the center of this bell curve. So this is where our sample p hat can be found, 0.7576, somewhere to the right hand side of the bell curve. And from now, at this point, as a next step, after realizing that our sample is particularly on the bell curve and to the right hand side of the bell curve center, in the next step, I am going to calculate the z-score of our sample. Z-score of our sample, indicating that with a subscript p hat right here, it's just my optional notation right here, but just z-score. The point now is that we're calculating the z-score for our sample value, for our sample proportion from where it stands on this bell curve that we have found. So the z-score here is 0.7576 minus 0.3, and we're dividing by the average spread, the standard deviation on this bell curve. The value already calculated to be 0.0230. So I'm dividing that difference here by 0.0230. Calculation of mine showed a z-score being positive 19.9. And so for z-scores, I usually round to 2 decimal places. And in this case particularly, we are forced to round down to only 1 decimal places. But do watch for your rounding requirements in each of the problems that you're doing. The z-score here is again a positive z-score, and allow me to write that in red ink. So after calculating the z-score for our sample, again, this z-score reflects how far our sample value is from the center of this bell curve, where our sample value, the p hat value here, belongs to. The next step, being quite critical for our testing hypothesis problem, is to calculate the p-value of our sample. So p-value here in this problem, in order for us to calculate p-value, we are going to set up the probability that on this bell curve, we're going to find a sample proportion that's anywhere greater than or equal to 0.7576. So in symbolic statements, probability that we're going to find a sample proportion at size 396 to be greater than or equal 0.7576. So this is how we set up the calculation for p-value. So p-value is the next step. Allow me to take a quick pause here and explain why I'm using the right tail inequality. I'm using the inequality that's pointing to the right-hand side simply because the test that we have concluded earlier indicating that we have to use a right tail test. And with our test indicated as a right tail test. Now in our step calculating the p-value, we must set up the problem here as with the inequality pointing to the right-hand side. And so now as a picture that you have seen me drawing that earlier, the picture here on this bell curve is the picture of an area pointing to the right-hand side from where our sample is. And that is the reason why this test here is called a right tail test. So as a connection, right tail test leads us into using the right-hand side, the inequality that points to the right-hand side. But then as the reason we call it right tail, because now when we're looking at the picture, it's a shaded area to the right-hand side from where our sample is. So this is how we must calculate our p-value. But now once we know that we can do this problem on the bell curve as a bell curve problem, then answering this probability where we're looking for p hat 396 greater than or equal to 0.7576 is exactly the same as finding the probability on our standard normal distribution curve where z-score is greater than or equal to the z-score 19.9, because from where our sample stands, it is the same as the z-score 19.9. So on the standard normal distribution curve, we're looking for the chance, the probability where our z-score is greater than or equal 19.9. And in order to calculate this p-value, in order to find this probability answer right here, we are now running our normal CDF command from a calculator. And I am about to use the standard TI, the calculator where the name of the command is exactly like this, normal CDF command. But if you choose to use any other calculator, then you must read the user manual to find out what command will do the similar functionality here. And so now on my calculator here, to find a normal CDF command, we're gonna go second variables, which will bring up the menu for all the distribution functions here. And so normal CDF command is found right here. I'm going to use the down arrow key to select that particular command, and now I'm going to put it on screen. I'm going to hit enter. For anyone who has a TI-83 or an earlier TI-84 calculator, when you run second variables, which will bring up your normal CDF command, instead of seeing a menu as you have seen earlier, you will see the command being directly printed on your screen as seen here. And so now let's proceed. In this problem, our area is shaded to the right-hand side of a given value. That means we have a definite low end. So in this case, the lower end here is positive 19.9. I'm going to hit enter to come down to the upper limits of our interval, and now it's going to be positive 1E99. So 1E99. And in the way how I teach my stats students, I always want any one of my students to default the normal CDF command to 0 for mu and 1 for sigma. In other words, we only, at least for my class, we only use a normal CDF command to find answers from a standard normal distribution curve. And so now, having all of these information ready, I'm going to hit enter a few times. And just like that, for students who have an earlier calculator where it only shows the command right on your screen instead of the menu like you have seen earlier, then you're just going to type in manually the values, the low end, the high end, separated by a comma, and then comma, the center of your bell curve, which is a lot of time for my class, 0, and comma 1, which is standard deviation for our bell curve, and then we close the parentheses. And now we're going to hit enter. So this is the how big that area is that I shaded on the bell curve right here. So on my writing board, let's complete our written normal CDF command here. So low end here is a 19.9. High end, I'm going to indicate 1E99. And I'm going to default center of my bell curve to 0 and standard deviation 1. The answer we have seen earlier on the calculator screen is a 2.1957 and a lot longer with the E minus 88. This answer here, that's just the way how the calculator is putting the result, but this answer means our answer truly was 2.1957 and a lot longer times 10 to the minus 88 power, which now in decimal just really means 0.0000 and a lot longer. And all of these telling values are 87 zeros before the 88th one being the non-zero digit. And so now rounding to 4 decimal places, our final p-value is concluded to be 0.000. So now that we have calculated our p-value for this test, now we're going to need to decide whether this p-value is going to give us strong evidence in our sample. So we're going to compare our p-value 0.000 with the significance level given in the problem. So now back to the wording description of the problem. I'm going to clear out some of the highlights earlier. The significance level given in the problem is indicated right here in our problem. So at significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is more than 30%. So we have found a p-value, but how do we know if this p-value can indicate for us whether our sample is showing strong evidence? So the decision line is here. We are going to compare our p-value with the significance level. In our problem, it's 0.01. So this p-value is well below our significance level. So this comparison between the p-value and the significance level, right from that step right here, which is important. So p-value is what we calculated, and the comparison here we're comparing with what's given from the problem as significance level. So now right from that comparison, we come to the following conclusion. So I use arrow over here to indicate that from our calculation leads to the conclusion as following. The sample proportion that we're using here, that value 0.7576 is an unlikely sample. And in a more advanced course in statistics, I should be able to point out what it means exactly by being an unlikely sample and how being an unlikely sample leads to having strong evidence. But here we simply just take that as a rule that anytime we prove that our p-hat, our sample being an unlikely sample, then it immediately leads to the next important understanding or conclusion that our current sample that we're using, the lowercase p-hat right here, the sample proportion, is showing, or for a lot of times you can just say directly p hat is a strong evidence. The sample we have itself is strong evidence. But strong evidence for what? Strong evidence to support whoever making that statement, the proportion of iPhone users should be above 0.3. So another way of saying to support, we have strong evidence p hat here showing strong evidence to support H1. Or alternatively, we can also say p hat is showing strong evidence, or p hat, our sample proportion, is strong evidence to reject H sub 0. And I gave all of that complete explanation in our general video lecture. The idea now is that when we have strong evidence, that means once we support H1, that means we are rejecting H sub 0. And equivalence way of the equivalence logic is going the other way around. If we are rejecting H sub 0, that means we are supporting H1. We're leaning toward H1. And then just like how I explained in the general lecture, our question here of any testing hypothesis problem is a yes or no question. Look at the structure of the question itself one more time here. Is the sample showing strong evidence? Is the sample here showing strong evidence? Apparently we just made that statement. The sample is showing strong evidence, either to support H1 or to reject H sub 0. So ultimately speaking, the answer to our yes or no question is now a yes. Our sample is showing strong evidence to support H1 or to reject H sub 0. So now that we have finished carrying through all the steps that need to be done in order to prove that our sample showed strong evidence to either reject H sub 0 or to support H sub 1 as the two hypotheses here. And so ultimately we answer yes to the question as in whether or not our sample was showing strong evidence. So yes, we knew that our sample was showing strong evidence based on the p-value that we have calculated here. So as I said earlier, now allow me to get back and give some further remarks on this particular step right here, where mainly what I did here was to multiply the sample size with the value of the proportion claimed in the null hypothesis. And the same sample size I would also multiply with 1 minus the population proportion stated in the null hypothesis. So allow me now to give a remark of why we need to have that step carried out. So if we look through the entire structure over here, the steps where we calculate the p-value is a vital step. It's a very critical and vital step right here. This p-value is what helps us decide whether we have strong evidence or not. That depends on the calculation of the p-value. However, if we now look even further and look closely, or you may even want to roll back in the video and view how I carried out the steps. The main key to find the main key for us, or in order for us to be able to calculate this p-value or to come to this final p-value, the main key is that we put our sample proportion on a bell curve. And so, but now if we're looking a little further, how did we know in the first place that we are able to, or how did we know in the first place that we would be able to put our sample to be on a bell curve? Or in another way of saying, how would we know if our sample here, our sample proportion here, is a sample value of a distribution that is on a bell curve? So without this bell curve, we wouldn't even be able to perform this calculation. Or in another way of saying, without having this bell curve right here, we won't even know whether we can use the normal CDF command, because everything we're doing here was based on the understanding about the bell curve. And so This step now becomes vital, become very critical, important step before we draw the bell curve for all of our sample proportions, simply because this step, once our sample size has passed the two requirements, the sample size multiplying with the proportion claimed in the null hypothesis being a value above 10, and as well as the sample size multiplied with 1 minus the proportion value claimed in the null hypothesis, as long as both of those products come up with a count above 10, and that's why I put check mark here. So as long as our sample size satisfies the two requirements here, then we know that all of our sample proportions, including the one that we already have, can be placed on a bell curve, and particularly or specifically our particular sample proportion will be on a bell curve, and from there we can carry on with the calculation of the p-value entirely as a bell curve problem. And that is the reason why this step of verifying the sample size is so important. And so anyone viewing the lesson here may also start concerning, so what if, let now allow me to come up with a different scenario. What if our sample size is only 10, and in our sample proportion we come up with something such as, how about 7 out of 10? So with the claim stating that the proportion is equal to 0.3, and alternative hypothesis stating that proportion of iPhone users is above 0.3. So I'm creating a scenario where we want to find out an answer to that concern about what if the sample size we used here does not satisfy the requirements. Because apparently the sample size being 10, once multiplied with 0.3, again the value claimed in the null hypothesis, this only gives us a count of 3, which fails being above 10. As I said, fails being above 10. 3 does not appear to be greater than 10. 3 is not greater than 10. And as well as, and also the same sample size. Now that once we multiply that with 1 minus 0.3, it also comes out with a product being 7, which is again failed to be greater than 10. I could have written these as less than 10 and less than 10, but I want to point out that we always want these products to be greater than 10, and with a sample size like this, our sample failed this checking requirements right here. So now what? So what if we fail this requirement? So failing this requirements, the reason I have to mention about this is that failing this requirements simply failing the requirements, or how about the sample size requirements? Will make the p-value calculation incorrect. And this is the major reason why we have to have a sample that's passed. So failing the sample size requirements will make the p-value calculation incorrect. And so in that way, think about in the practical situation, if we really end up with a sample, if we really have a sample that fails the requirements, then there are two options for us. If the sample size fails the requirements, then there are two options for us. Option number one right here, we just stop the testing hypothesis or stop the testing procedure, because we won't be able to proceed any further. Or option number 2, we have to find a different sample where sample size meets the requirements.